An Egyptian fraction is a finite series of distinct unit fractions, such as, that is, each fraction in the expression has a numerator equal to 1 and a denominator that is a positive integer, and all the denominators differ from each other. The value of an expression of this type is a positive rational number a, b. For instance, the Egyptian fraction above sums to 43/48. Every positive rational number can be represented by an Egyptian fraction. Sums of this type, and similar sums also including 2/3 and 3/4 as summands, were used as a serious notation for rational numbers by the ancient Egyptians, and continue to be used by other civilizations into medieval times. In modern mathematical notation, Egyptian fractions have been superseded by vulgar fractions and decimal notation. However, Egyptian fractions continue to be an object of study in modern number theory and recreational mathematics, as well as in modern historical studies of ancient mathematics. Motivating applications. Beyond their historical use, Egyptian fractions have some practical advantages over other representations of fractional numbers. Comparing the size of some fractions, Egyptian fractions sometimes make it easier to compare the sizes of a pair of fractions. For example, if one wants to find out whether 4/5 is larger than 3/4, one could convert them to Egyptian fractions with shared parts. 4/5 equals 1/2 plus 1/4 plus 1/20. 3/4 equals 1/2 plus 1/4. Hence, 4/5 is larger by 1/20. Similarly, comparing 3/11 and 2/7. 3/11 equals 1/4 plus 1/44. 2/7 equals 1/4 plus 1/28. As 1/44 less than 1/28, this implies that 3/11 less than 2/7. Equally distributing objects, Egyptian fractions can help in dividing a number of objects into equal shares. For example, if one wants to divide 5 pizzas equally among 8 diners, the Egyptian fraction 5/8 equals 1/2 plus 1/8, means that each diner gets half a pizza plus another eighth of a pizza, e.g., by splitting 4 pizzas into 8 halves, and the remaining pizza into 8/8. Similarly, although one could divide 13 pizzas among 12 diners by giving each diner one pizza and splitting the remaining pizza into 12 parts, one could note that 13/12 equals 1/2 plus 1/3 plus 1/4, and split 6 pizzas into halves, 4 into thirds and the remaining 3 into quarters, and then give each diner 1/2, 1/3 and 1/4. Early history. For more information on this subject, see Egyptian numerals, Eye of Horus, and Egyptian mathematics. Egyptian fraction notation was developed in the Middle Kingdom of Egypt, altering the Old Kingdom's Eye of Horus numeration system. 5 early texts in which Egyptian fractions appear were the Egyptian mathematical leather roll, the Moscow mathematical papyrus, the Reisner papyrus, the Kahun papyrus and the Akhmim wooden tablet. A later text, the Rind mathematical papyrus, introduced improved ways of writing Egyptian fractions. The Rind papyrus was written by Ahmes and dates from the Second Intermediate Period. It includes a table of Egyptian fraction expansions for rational numbers chapter 2, n, as well as 84 word problems. Solutions to each problem were written out in scribal shorthand, with the final answers of all 84 problems being expressed in Egyptian fraction notation. 2. N tables similar to the one on the Rind papyrus also appear on some of the other texts. However, as the Kahun papyrus shows, vulgar fractions were also used by scribes within the calculations notation to write the unit fractions used in their Egyptian fraction notation, in hieroglyph script. The Egyptians placed the hieroglyph above a number to represent the reciprocal of that number. Similarly, in hieratic script they drew a line over the letter representing the number. For example, the Egyptians had special symbols for 1/2, 2/3, and 3/4 that were used to reduce the size of numbers greater than 1/2 when such numbers were converted to an Egyptian fraction series. The remaining number after subtracting one of these special fractions was written using as a sum of distinct unit fractions according to the usual Egyptian fraction notation. The Egyptians also used an alternative notation modified from the Old Kingdom and based on the parts of the Eye of Horus to denote a special set of fractions of the form 1/2 k and sums of these numbers, which are necessarily dyadic rational numbers. These Horus I fractions were used in the Middle Kingdom in conjunction with the later notation for Egyptian fractions to subdivide a hakat, the primary ancient Egyptian volume measure for grain, bread, and other small quantities of volume, as described in the Akhmim wooden tablet. If any remainder was left after expressing a quantity in Eye of Horus fractions of a hakat, the remainder was written using the usual Egyptian fraction notation as multiples of a row, a unit equal to 1/320th of a hakat. Calculation methods. Modern historians of mathematics have studied the Rhind papyrus and other ancient sources in an attempt to discover the methods the Egyptians used in calculating with Egyptian fractions. In particular, study in this area has concentrated on understanding the tables of expansions for numbers of the form 2n in the Rhind papyrus. Although these expansions can generally be described as algebraic identities, the methods used by the Egyptians may not correspond directly to these identities. Additionally, the expansions in the table do not match any single identity, rather, different identities match the expansions for prime and for composite denominators, and more than one identity fits the numbers of each type. For small odd prime denominators p, the expansion 2p equals 2 plus 2p was used. For larger prime denominators, an expansion of the form 2p equals 1, a plus ap was used, where a is a number with many divisors between p2 and p. The remaining term, ap, was expanded by representing the number ap as a sum of divisors of a and forming a fraction d ap for each such divisor d in this sum. As an example, Ahmed's expansion 1/24 plus 1/111 plus 1/296 for 2/37 fits this pattern with a equals 24 and ap equals 11 equals 3 plus 8. As 1/24 plus 1/111 plus 1/296 equals 1/24 plus 3 plus 8. There may be many different expansions of this type for a given p. However, as K. S. Brown observed, the expansion chosen by the Egyptians was often the one that caused the largest denominator to be as small as possible. Among all expansions fitting this pattern, for composite denominators, factored as p times q, one can expand 2pq using the identity 2pq equals 1, aq plus 1, apq, where a equals 2. Some authors have preferred to write this expansion as 2a times a pq, where a equals p plus 1, replacing the second term of this product by pq plus 1, pq. Applying the distributive law to the product, and simplifying leads to an expression equivalent to the first expansion described here. This method appears to have been used for many of the composite numbers in the Rhind papyrus, but there are exceptions, notably 2/35, 2/91, and 2/95. One can also expand 2pq as 1pr plus 1qr, where r equals 2. For instance, Rms expands 2/35 equals 1/30 plus 1/42, where p equals 5, q equals 7, and r equals 2 equals 6. Later scribes used the more general form of this expansion, n, pq equals 1, pr plus 1, qr, where r equals n, which works when p plus q is a multiple of n. For some other composite denominators, the expansion for 2pq has the form of an expansion for 2q with each denominator multiplied by p. For instance, 95 equals 5 times 19, and 2/19 equals 1/12 plus 1/76 plus 1/114, so 2/95 equals 1 plus 1 plus 1 equals 1/60 plus 1/380 plus 1/570. This expression can be simplified as 1/380 plus 1/570 equals 1/228, but the Rind papyrus uses the unsimplified form. The final expansion in the Rind papyrus, 2/101, does not fit in any of these forms, but instead uses an expansion to p equals 1, p plus 1/2, p plus 1/3, p plus 1/6 p that may be applied regardless of the value of p. That is, 2/101 equals 1/101 plus 1/202 plus 1/303 plus 1/606. A related expansion was also used in the Egyptian mathematical leather roll for several cases. Later usage. For more information on this subject, see Liber Abbasi and Greedy algorithm for Egyptian fractions. Egyptian fraction notation continued to be used in Greek times and into the Middle Ages. Despite complaints as early as Ptolemy's Almagest about the clumsiness of the notation compared to alternatives such as the Babylonian Base-60 notation, an important text of medieval mathematics, the Liber Abbasi of Leonardo of Pisa, provides some insight into the uses of Egyptian fractions in the Middle Ages, and introduces topics that continue to be important in modern mathematical study of these series. The primary subject of the Liber Abbasi is calculations involving decimal and vulgar fraction notation, which eventually replaced Egyptian fractions. Fibonacci himself used a complex notation for fractions involving a combination of a mixed radix notation with sums of fractions. Many of the calculations throughout Fibonacci's book involve numbers represented as Egyptian fractions, and one section of this book provides a list of methods for conversion of vulgar fractions to Egyptian fractions, if the number is not already a unit fraction. The first method in this list is to attempt to split the numerator into a sum of divisors of the denominator. This is possible whenever the denominator is a practical number, and Liber Abbasi includes tables of expansions of this type for the practical numbers chapter 6, 8, 12, 20, 24, 60, and 100. The next several methods involve algebraic identities, such as, for instance, Fibonacci represents a fraction by splitting the numerator into a sum of two numbers, each of which divides 1 plus the denominator. Fibonacci applies the algebraic identity above to each these two parts, producing the expansion. Fibonacci describes similar methods for denominators that are 2 or 3 less than a number with many factors. In the rare case that these other methods all fail, Fibonacci suggests a greedy algorithm for computing Egyptian fractions, in which one repeatedly chooses the unit fraction with the smallest denominator that is no larger than the remaining fraction to be expanded. That is, in more modern notation, we replace a fraction x, y by the expansion where represents the ceiling function. Fibonacci suggests switching to another method after the first such expansion, but he also gives examples in which this greedy expansion was iterated until her complete Egyptian fraction expansion was constructed. And as later mathematicians showed, each greedy expansion reduces the numerator of the remaining fraction to be expanded, so this method always terminates with a finite expansion. However, compared to ancient Egyptian expansions or to more modern methods, this method may produce expansions that are quite long, with large denominators, and Fibonacci himself noted the awkwardness of the expansions produced by this method. For instance, the greedy method expands, while other methods lead to the much better expansion. Sylvester's sequence 2, 3, 7, 43, 1807. can be viewed as generated by an infinite greedy expansion of this type for the number 1, where at each step we choose the denominator instead of, and sometimes Fibonacci's greedy algorithm is attributed to Sylvester. After his description of the greedy algorithm, Fibonacci suggests yet another method, expanding a fraction by searching for a number C having many divisors, with replacing by, and expanding as a sum of divisors if, similar to the method proposed by Huch and Bruins to explain some of the expansions in the Rhind Papyrus. Modern number theory. For more information on this subject, see Erdos-Graham conjecture, ZNAM's problem, and Engel expansion. Although Egyptian fractions are no longer used in most practical applications of mathematics, modern number theorists have continued to study many different problems related to them. These include problems of bounding the length or maximum denominator in Egyptian fraction representations, finding expansions of certain special forms or in which the denominators are all of some special type, determination of various methods for Egyptian fraction expansion, and showing that expansions exist for any sufficiently dense set of sufficiently smooth numbers. One of the earliest publications of Paul Erdos proved that it is not possible for a harmonic progression to form an Egyptian fraction representation of an integer. The reason is that, necessarily, at least one denominator of the progression will be divisible by a prime number that does not divide any other denominator. The Erdos-Graham conjecture in combinatorial number theory states that, if the unit fractions are partitioned into finitely many subsets, then one of the subsets has a subset of itself whose reciprocals sum to 1. That is, for every r greater than 0, and every r coloring of the integers greater than 1. There is a finite monochromatic subset S of these integers such that the conjecture was proven in 2003 by Ernest S. Crute. 3. ZNAM's problem and primary pseudo-perfect numbers are closely related to the existence of Egyptian fractions of the form. For instance, the primary pseudo-perfect number 1806 is the product of the prime numbers chapter 2, 3, 7, and 43, and gives rise to the Egyptian fraction 1 equals 1/2 plus 1/3 plus 1/7 plus 1/43 plus 1/1806. Egyptian fractions are normally defined as requiring all denominators to be distinct, but this requirement can be relaxed to allow repeated denominators. However, this relaxed form of Egyptian fractions does not allow for any number to be represented using fewer fractions, as any expansion with repeated fractions can be converted to an Egyptian fraction of equal or smaller length by repeated application of the replacement. If k is odd, or simply by replacing 1, k plus 1, k by 2, k if k is even. This result was first proven by Takenuchi. This method can lead to long expansions with large denominators, such as Botts had originally used this replacement technique to show that in any rational number has Egyptian fraction representations with arbitrarily large minimum denominators. Any fraction x, y has an Egyptian fraction representation in which the maximum denominator is bounded by, and a representation with at most terms. It is known that terms may sometimes be needed, and conjectured that Voss's bound can be improved too. It is also possible to find representations in which both the maximum denominator and the number of terms are small. Graham characterized the numbers that can be represented by Egyptian fractions in which all denominators are nth powers. In particular, a rational number q can be represented as an Egyptian fraction with square denominators if and only if q lies in one of the two half-open intervals. Martin showed that in any rational number has very dense expansions, using a constant fraction of the denominators up to n for any sufficiently large n. Engel expansion, sometimes called an Egyptian product, is a form of Egyptian fraction expansion in which each denominator is a multiple of the previous one. In addition, the sequence of multipliers I is required to be non-decreasing. Every rational number has a finite angle expansion, while irrational numbers have an infinite angle expansion. And Schell and Goldfeld study numbers that have multiple distinct Egyptian fraction representations with the same number of terms and the same productive denominators. For instance, one of the examples they supply is, unlike the ancient Egyptians, they allow denominators to be repeated in these expansions. They apply their results for this problem to the characterization of free products of abelian groups by a small number of numerical parameters: the rank of the commutator subgroup, the number of terms in the free product, and the product of the orders of the factors. Open problems. For more information on this subject, see odd-greedy expansion and Erdos-Strauss conjecture. Some notable problems remain unsolved with regard to Egyptian fractions, despite considerable effort by mathematicians. The Erdos-Strauss conjecture concerns the length of the shortest expansion for a fraction of the form 4n. Does an expansion exist for every n? It is known to be true for all n less than 1014, and for all but a vanishingly small fraction of possible values of n. But the general truth of the conjecture remains unknown. It is unknown whether an odd-greedy expansion exists for every fraction with an odd denominator. If Fibonacci's greedy method is modified so that it always chooses the smallest possible odd denominator, under what conditions does this modified algorithm produce a finite expansion? An obvious necessary condition is that the starting fraction x, y have an odd denominator y, and it is conjectured but not known that this is also a sufficient condition. It is known that every x, y with odd y has an expansion into distinct odd unit fractions, constructed using a different method than the greedy algorithm. It is possible to use brute force search algorithms to find the Egyptian fraction representation of a given number with the fewest possible terms or minimizing the largest denominator. However, such algorithms can be quite inefficient. The existence of polynomial time algorithms for these problems, or more generally the computational complexity of such problems, remains unknown. Guy describes these problems in more detail and lists numerous additional open problems.